tell us about how to understand random Reed-Solomon, other large alphabet codes.
Mostly Reed-Solomon. Also random linear codes. Yeah, okay, so some large alphabet codes. Okay, cool. I encourage you to, like, you can really feel free to ask questions. If you, I mean, you do ask. It's like it's not. Don't see this as you're not doing anything wrong. I'm just saying, like, continue asking questions. It's great. Okay, so we have our types framework, and okay, so now I'm going to take this. So as I said, like, there's the way that AGL proved the theorem, which is so they worked directly on random Reed-Solomon codes, and I think implicitly they have a types framework which is similar to this, except I think you guys didn't in your implicit type system. I think you don't have the row span as part of your types. That's the main difference between my viewpoint and your viewpoint, I think. And they worked on that directly. I'm going to, for intuition, or not just for intuition, the way I think about this is first proving that random linear codes achieve the list decoding GV bound when Q is large. And then somehow using this intuition to reason about Reed-Solomon codes as well. I mean, there's going to be a reduction here from random linear codes to Reed-Solomon codes. Yeah, and I'll try to, when it's viable, I'll try to compare, like, my presentation with what appears in with what AGL did, and like. Okay. So let's fix a type. Okay, so this is going to be a type over 3, just with locality 3. Okay, so we have 3 vectors, and the row span is going to be f3 to the n. F3 to the n means that, right, like, if the rows span everything. So think of a matrix where, right, so you have this matrix with x1, x2, and x3. The rows span everything. That means that there are no non-trivial linear relations between x1, x2, and x3. So that's like the generic case. And we fix a sequence of partitions for a type. So, in this row, x1 needs to be equal to x2. In this row, x1, x2, and x3 all need to be equal. In this row, there's nothing. We don't put any constraints on equality, and so forth.
Do you really mean f3 to the n? Don't you mean f?
You're right. This should be an L. That's the second time I was caught with the wrong. That's an important one. That's the second time I was caught with the wrong exponent in these. Yeah. So that should be. That's the FQ to the L, not F3 to the. Oh my God. Yeah, that's embarrassing. Yeah, FQ to the 3. Okay. Yeah. Thank you. Okay. Okay, and we want to know for this type is okay. So right. So we're implicitly now doing a union bound over type. So now the question has been reduced to we're given a type. For example, this is not a generic type because there's an FQ to the 3 here. But so it's like we also need to consider types where there are relations between x1, x2, and x3. But for this example, we're going to assume that there are none. And we wanted to try and bound the probability that a random linear code contains any matrix of this type. So first, the intuition is that how many candidates are there? So, right, so there are q to the Rn code words. So there are roughly q to the 3 Rn triplets of code words that are candidates here. Why do I say roughly? Because a small number of these triplets have some non-trivial relations between them. For example, the triplet x1, x1, x1 is obviously has some non-trivial linear relations. So it's not viable for it's not viable for being belonging to this type. But almost every triplet of code words that we take is going to have no non-trivial linear relations. So this is the number of triplets involved. And now the question is, okay, so what's the probability that such a triplet, or how many such triplets do we expect to satisfy the partitions, these partitions? So now that each partition imposes an x1, x2, and x3, it imposes some linear conditions. Okay? How many conditions? 3 times the size of the number of partitions, right? So here the number, here the size of pi of the partition itself is 3. There are 3 classes, and it doesn't pose any condition. Here there's 1 class, so it really imposes 2 linear conditions. X1 needs to equal x2, and x1 needs to equal x3 in this coordinate. And here it imposes 1 condition. X1 needs to equal x3. Okay. So we can define the degree of this type as the amount of freedom that we have, which is 3Rn degrees of freedom in choosing triplets, minus the amount of minus the number of conditions. And then, if this degree is less than 0, then this is easy to show by a first moment argument for random linear codes. In a random linear code, there's probably going to be no matrix of this type in the code. This is specifically for a random linear code. This is not easy at all to show something similar for, say, a Reed-Solomon code. But for a random linear code, this specific part is easy. Okay. And now, so this is kind of going to be the analog of. I mean, this can also really be. This is really the exponent of some expectation. Okay, so this is really, if you remember what we did in the previous, the classic types framework, right? We looked at the expectations and we said, okay, if the expected number of elements of the type in the random linear code goes to 0, then with high probability, this type is not going to be contained in the code at all. And now the question is in the other direction. Suppose that this degree is positive. Okay, so an expectation, there are many triplets. Does that mean that with high probability, the random linear code is going to contain such a triplet? Okay, so it's the same question we asked before. What if the degree is large? Okay, this is red because this seems like a bad thing. Why is this a bad thing? Because we don't want to contain, like a good code does not contain these triplets because these triplets are bad. So the large degree has a sense of something bad looming for us. So would there be a triplet belonging to the type T in the code? So here's a pretty simple observation. There must be non-trivial triplets in the code which satisfy P. Non-trivial means not all 0. Why is that? Because the degree is really, right, so we have, the degree is just like the number of, the degree is the number of degrees of freedom minus the number of linear constraints. If there are more degrees of freedom than linear constraints, then there are non-trivial solutions, always. It's not probabilistic, it's just a fact. Okay. But that doesn't necessarily mean that there is a triplet of the given type in the code. And why is that? Because the row span, it's not necessary that the row span be fq to the 3. Okay, so it's possible to have, and we're going to show an example later. It's possible to have sets of constraints, like sequences of constraints, where we will have non-trivial solutions, but all these non-trivial solutions are gonna have some non-trivial linear relation between them. And just to give you an example of what can be such a linear solution, it's possible, for example, that they're not even distinct. So it's possible that there do exist non-trivial solutions, but in each of them, x1 is equal to x2, which really defeats the purpose, right? I mean, in our types, we're always looking for tuple, like we always look for tuples of distinct code words. So if each of these non-trivial solutions has x1 equal to x2, then obviously this is not really this is not considered as the type being contained in the code. Okay, so what I'm saying here, like the takeaway from this is that it's possible that the degree is large. Okay, we expect a large number of we expect an expectation we're going to have a lot of elements of the given type in the code, but in actuality, with high probability, we're not going to contain even a single one, which is really the same as what we had in the classic types framework. Okay. Yes.
I mean, doesn't this even hold, like, the case that they're all the same? Couldn't that even hold when the degree is negative? So,
If the degree is negative, okay, all I'm saying about the case where the degree is negative is that in that case, you're not going to get, like, in a random linear code with high probability, you're not going to get a triple satisfying all the constraints with no linear relations between them. Yes, you could get a triplet in which like x1 is always equal to x2. Yeah, it's possible. Yes.
so, but somehow the first moment method can account for that, or?
Yeah, we're going to like we're going to be discussing exactly that. Yeah, like yeah, you're gonna get an idea of what this sort of thing really looks like in random linear code. Okay. So here's an example of what I just gave, of what I just mentioned. Okay, so here I put a list of constraints. Okay, so just notice that almost all of the constraints, like the third coordinate is not involved in any constraint, and almost all of the coordinates, and also all of the coordinates x1 needs to equal x2. So what happens here? If the rate is large enough, then the degree can be positive. Like if the rate is, I don't know, like 3/4 or something, then just because 3 is never involved, like it gives us a lot of degrees of freedom. So the degree is going to be large. However, it's very likely that all the solutions will have x1 equal to x2. Because, for example, assume that this is the only place where we don't want x1 to equal x2. Okay, we don't need them to equal each other. Then any solution here would need to have x1 and x2 differ from each other by, at most, like have a Hamming distance at most 1. And we know that a random linear code is probably not going to have distance 1. So in all likelihood, we're not going to get solution, even though we're going to get solutions because the degree positive, we're not going to get solutions for which x1 is equal to x2. Okay. Okay. So we're building into like a statement of what does happen. Okay, we're going to get like this pretty clean statement that explains what types we can actually expect to see in our code. So next I'm going to ask, what about a type of this form? Okay, so now again we have some constraints, a list of constraints, a list of partitions. But now I want x1, x2, and x3 to satisfy some non-trivial relation. So what non-trivial relation do I want? It's probably even written on the board, right? Yes. I want 2x3 to equal x1 plus x2. Okay, so now I'm looking for, the type I'm asking about, triplets that, x1 plus x, this needs to hold in every coordinate. Here I wrote this correctly, fq to the 3, yes, okay. I was afraid that this is going to be a running mistake throughout the whole presentation. Okay, so I'm only going to look for triplets that satisfy this. And now, what's the degree of this type with this additional requirement? So on one hand, we have less degrees of freedom because we added a linear constraint. Now we have 2 degrees of freedom instead of 3 once I set right, the first 2 columns. The third one is going to be determined. So that seems like the degree should go down. So is this good for anything? Like, from an adversarial point of view, right? The adversary wants types to appear. So why would an adversary want to impose any sort of constraint like this? It seems to just decrease the amount of freedom, but it can also decrease the number of constraints. So why is that? Because note that in this relation, suppose that z1 equals z2, okay? Then, or here, suppose that in some coordinate, like this and this are identical. So you get like 2x3 equals 2x1, so x3 equals x1. Okay? So the constraint v means that wherever z1 equals z2, z1 is also going to equal z3. So that means that this sort of partition, 1, 2, 3, now becomes 1 constraint instead of 2. Okay? Because the 1 equals 2 already gives us the 1 equals 3 as well. Okay? So what this does, like I'm imposing this v, on one hand, we remove our n degrees of freedom. On the other hand, we remove a number of constraints. How many constraints exactly did we remove? That depends on the structure of this list here. If there are many constraints that look like this, 1, 2, 3, then the number of constraints has went down considerably, possibly more than the amount of degrees that we lost. Okay? So the degree, the thing is that the degree of this type, it may considerably, it can be larger than the degree of the type without this imposition of v, and it can be smaller. Both are possible. Okay. And this is just formally saying what would be the number of degrees of freedom that we have now, right? So in general, if we want the row span to consist, if we want to impose it, the row span needs to be v, but the number of degrees of freedom that we have is the dimension of v times Rn. So for example, if we impose this specific constraint, then the dimension was 2 after imposing this constraint. So we had, this was 2Rn minus, right, so when given that we are living inside the space V, okay, then a constraint such as say 1, 2, 3, what's the dimension of the constraint that actually imposes within V? It's the dimension of V minus the dimension of the intersection of V and the space of rows that satisfy this constraint. Okay? And if in a specific case where V is just the entire space, if it's fq to the 3, then this would be just sum of 3 minus the dimension of VPI, which is, yeah, very good. Yeah, we're okay. Sorry. Yeah, it's exactly what we had when we were when we originally defined this. I'm just saying that this notion of degree coincides with the notion of degree that we gave before for the specific case where V is the entire space. Okay, so now I can give you the relevant threshold theorem. Okay, so here's when a random linear code is likely to contain the matrix of a given type. So what we want is for the degree of this type with V to be larger, and there really needs to be a small gap here. I mean, I always, okay, throughout this entire talk, I use, inequality constraints, and there's always going to be some plus epsilon n here everywhere, okay? But in order for the probabilities to actually make sense. But imagine that the degree of P with the constraint V is larger than the degree of P with the, with any sub-constraint, okay? Any further constraint on the relations between x1, x2, and x3 needs to have smaller degree, less degrees of freedom. If this is the case, then we expect a matrix of type PV to appear. And I'll try to give the intuition for why this is correct. Okay, I'm guessing this is something you don't see immediately, right? So maybe the first question should be, okay, so this is an if and only if. So let's start with assuming that the degree of PV is less than the degree of PU. And here's what we're going to do now. So, do you remember the matrices? Okay, do you remember in the classic framework, we used the fact that in order for the code to contain a matrix, it also needs, like, if A is in C, then we also have AB belongs to C for all B and FQ to plus 1. That's the D. So we're also going to use that here. The way we're going to use that is as follows. So suppose that this is the case, okay? And U, I remind you that U is a proper subspace of V. So take B to be, okay, so we think of this B as this B, think of it for a second as a linear transformation from V to some smaller space, okay? Because we apply it to the vector, like we apply it to the rows of a matrix of this type. So these are rows that all belong to V, and we apply it, and we are going to project them onto some smaller space. How exactly are we going to choose B? We're going to choose B so that the kernel of B, maybe to simplify things, let's assume that V, I realize that this is better, just for the intuition. Let's assume that V is the entire space. Okay, that would clear up something that may be ambiguous here. Okay, so let's assume that V is the entire space, but it works the same if V is anything smaller. Okay, and let the kernel of B be U. Okay, so think of so what does B do? B is going to basically mod out U from, okay, we have 3 vectors. We're going to look at them modulo U. Okay. And now now we have the type of the matrices BA, of the matrices AB. Okay, so we have the set of all the matrices of the form AB. So consider this set, consider this new space. Let's call it TB. It's going to be the space of all the matrices AB, where A belongs to T. Yeah, where T is like this type. So we're just doing the same thing that we did in the classical case. Okay, we're defining this new set, which is what happens to a matrix here when we apply B to it, when we mod out U. And the thing is, just because of degree considerations, because the kernel plus the image equals the size of the ambient space, it's going to hold. So this is also a linear space. Okay. And there's also we can also define a degree for this type, just as we defined above. Okay, we can also think of this as a type, so we can also define a degree for this. And then we're going to have that the degree of TB is exactly equal to the degree of T minus the degree, like, yeah, the degree of t, let's call it the degree of p f to the third, okay, minus the degree of p with the kernel of b, which is 0. Okay, so the thing is that this type, its degree is exactly going to be this degree minus this degree. This is what happens when you mod out by u. Yeah.
Right, I'm having, pun intended, a type error. Wait, so b might possibly be small, be tall and skinny if little b is less than L plus 1.
B is always going to have less. Yeah, we always, yeah, B.
I think about it being tall and skinny.
Yes.
So then the matrices that live in TB might have little b columns, which is less than L plus 1 column.
Yes.
I see, but you've just...
It has little b columns, yes.
Okay, so then you said the degree of TB, but you haven't specified a partition. It can't be the same as P. That's
So defining the degree of TB is this is okay. This is not well defined. This is not something I defined. What exactly it means to be like. It's not defined by partitions. It's a slightly more complicated structure. But the point here is that the number of degree here is still going to be defined as the number of degrees of freedom minus number of constraints. It's still okay. Like the intuition for what does degree mean is still going to be the same. It's going to be degrees of freedom minus constraints. Okay, so the degree of TB is going to be the degree of this minus the degree of this, so it's going to be negative. Okay, and that means that in random linear code, we are going to expect there to be no, in random linear code, we're going to expect like that this is going to have, say, only the all zero solution for TB. Okay, so but if the only element of TB is the all zeros, then that means that every matrix A here in the code, when you apply B to it, you get 0. But if there's but that means so there's some non-trivial matrix that when you apply it to the rows of A, you always get 0. That means that the rows of A satisfy some non-trivial linear relation. And what we wanted, what we required here to begin with, is that there are no non-trivial linear relations. Okay. So this would be equivalent to the easy part of the threshold theorem in the classical case, because it shows that so having a degree PV less than degree PU means that with high probability PV does not appear in the random linear code. That's what it says. The other direction, that if this is larger for this for all subspaces, this is again proven by a second moment method, which is completely analogous to, it uses this same idea and the second moment method, and then it's completely analogous to how we proved the classical case and how Bolobash proved the case for graphs. It's all the same idea.
So you say that B was Q just for without loss of generality, or just
yeah, this is not it's just to avoid too much notation. That's everything. But this would hold for every V here. Okay, and I just want to know that in particular, right? So clearly, the degree should be positive, right? This is this is something we already said. If the degree is negative, when we don't expect this type to belong to the code. So how does that work with this characterization? Well, this condition in particular implies, this condition should in particular hold for u equals 0. But when u is just a 0, just like the trivial space, when the degree of P of the trivial space is 0, right? Because there's no degrees of freedom, but also all the constraints are trivially satisfied. So that would be a 0 here. So in particular, this condition posits that the degree of P with V is indeed positive, which seems, I'm saying this is as a sanity check for this condition. Okay, so this is our threshold theorem. And this, also to compare with the AGL work, this is why I insisted on having this V inside the type. Yeah. Okay. Great. So now we can use this this idea, or like this characterization, just like the easy part of this characterization. The thing is that the easy part of the characterization now is not that, like, is less trivial than it was before. Like, it's not that obvious, right? That like having this condition, like the deg PV less than deg PU means that PV is unlikely to appear. It's not as trivial as we had for the classical framework. But once you have that, it's actually not very hard to prove that random linear codes achieve the list decoding GV bound. So we proved this fact. This was already proven by AGL. AGL do this by, so some part of the theorem is by reduction to Reed-Solomon codes, or to the way they handle Reed-Solomon codes. I'm guessing this is an artifact of the fact that you guys thought a lot about Reed-Solomon codes and then ended up realizing that you can also do this for random linear codes. But we also use a key component that we took from you, which is the notion of I forgot what the initials mean. WPC. Well, or right? Was it? Sorry.
Weekly partition connected.
Yeah, weakly partition connected. Okay, so there's a combinatorial thing that you do, which the way I view it is just showing. I mean, in my view, I just use this your combinatorial idea to show that for every that if we are inside the parameters of the list decoding GV bound, then for every V there exists an U such that this inequality holds. Okay, so this I mean, so yeah, the way you do it is you think of it as something in terms of hypergraphs, but it ends up being like roughly the same. Okay, so this is a theorem that can be proven using this framework, but can also be proven, again, has already been proven in another way. And then we have, yeah.
Sorry, before you get to the reduction, for the just random linear codes bit, so you mentioned earlier that this sort of type notion works just fine for list recovery as well. Does this theorem also work fine for list recovery as well?
Unfortunately, no. That would have been, yeah, no. If that, yeah, this is specifically. You're right. I actually promised that I'm going to say throughout the talk what doesn't work for, like, everything I said from the introduction of these new types up to this point was correct also for list recovery and all other properties that you can express using these types. This doesn't.
And that's the combinatoric stuff.
That's. Combinatoric stuff doesn't, yeah, the combinatoric stuff doesn't work when you have, like, the thing is that in the list decoding case, you really only care, like, for a given coordinate, you only really care about, like, you have a partition, but you really care about only one set in the partition. When you care about multiple sets in the partition, then, yeah, you get a more complicated combinatorial structure for which the logic from AGL or from, yeah, all these papers doesn't work anymore. But I want to say that I haven't yet given enough thought to trying to reason about list recoverability of random linear codes with this framework. So I'm really hoping that it can be used to say something more substantial. Maybe just to give some idea about how much more difficult this is. We know that, okay, for list decoding, you really don't care what's the field, you just care about its size. Whereas for list recovery, we know that list recoverability of random linear codes is harder, at least we know that it's hard when the field is a prime, like is a power of a small prime. Like there's a difference, there's going to be a difference between a field size which is a power of 2 and a comparable size which is just a prime. And there's nothing in the current methods that can take into account differences like that. Okay. Cool. So this is one thing. And then the second theorem that we have this is the reduction from random linear codes to random read-Solomon codes. So if we have a local identity property, so now we're going back to list decoding and list recovery and everything together. So let P be a property that's achieved by a random linear code with high probability. Then it's also achieved with high probability by a random read-Solomon code, where the dependence, the field size is gonna have this, is gonna be like order of n, with some dependence on L, which is gonna be, it depends on the exact property, but it's gonna be at most like L to the L. Like for list recovery, this is gonna be L to the L. For list decoding, it's gonna be like 2 to the L. Okay. The reason for this difference is that for list decoding, again, we don't really care about the partition. We only care about one set in the partition, and there's 2 to the L possible sets. For list recovery, we care about the whole partition, so it's going to be L to the L. If you want, you can make this L to the little L, I think. Okay. Yeah, okay, so this is what we prove. I'm going to talk about this proof in a bit. Just let's get a corollary out of this before. So a random read-Solomon code achieves the list decoding GV bound with Q, I should have said with Q linear in M. And this is already being proven in the AGL paper. I'll say again something that compares our methods. So AGL uses a theorem called the GM-MDS theorem. And what they do, in my point of view, so they go over all the bad types. For each type, the GM-MDS theorem tells you, tell me if that makes sense. The GM-MDS theorem tells you for a given type that there exists a read-Solomon code that does not contain matrices of that type, that manages to avoid that type. And then they do an amplification, a probability amplification argument. They show that if there's one such read-Solomon code, then most read-Solomon, with overwhelming probability, this is going to happen for read-Solomon code. And the overwhelming probability allows them to do a union bound over the number of types. At least this is how I view your argument. But feel free to correct me now if you think I'm...
I mean, like, the JMDS theorem is used to, like, use it to, show that the intersection matrices have determinant symbolically non-zero. So you can use short symbol on that. Yeah. And then you just repeatedly you move like rows, and you really get a bunch of determinants, and each one you apply a short symbol on them.
Yeah.
Probability is multiplied.
Yeah, but like the way you use it, I think, why the determinant's non-zero? Because there exists one code which is good for that type, right?
Yeah, exactly.
Oh, yeah, okay, so...
But it's just to argue that some determinant, some polynomial is just symbolically non-zero.
Yeah. Yeah, so I see this as a probability amplification again, because I think like you use the fact that there's one good read-Solomon code, and then you show that almost every read-Solomon code is good for that specific type. But you need to do it. You need to union bound over types. Okay, maybe maybe I don't understand exactly. Like maybe there's a nuance here I'm missing. This is kind of the way I'm thinking about it. Okay. And we also get that a random read-Solomon code is at least as list recoverable as a random linear code. Now, there are many results. Most of them have Mary's name on them about list recoverability of random linear codes. We don't think we have the optimal one yet. But if one day we will, then that would also immediately apply to read-Solomon codes. Another question, by the way, that's been asked of me here, and I need to think about it. I don't have the answer on top of my head, is whether this reduction also works the other way around. Like, can you reduce from read-Solomon codes to random linear codes? Because it's possible that that's actually easier to reason about list recoverability of read-Solomon codes, and then we can say something about random linear codes given that. So both directions here are interesting. I think our methods also give a reduction in the other direction, but I'm not clear on that yet. So I'll update whoever is interested later.
So maybe I'm missing something trivial. It seems like if the list size grows, then Q grows. Is it because the gap to the GV bound also decreases or something like that?
So the reason you need that is because your locality, you need Q to be larger to. There are a few reasons you need Q to be larger, but I think the main one is just in order to do this union bound over the number of types. So you have more types, and as I showed before, the thing is that you allow yourself the number of types in order to union bound over them needs to be like Q to the epsilon n. So the way, because right, like an epsilon change in the rate allows you to overcome this number of types, Q to the epsilon n. So if you increase Q, this becomes larger, so you can do a union bound over more types. That's really the reason you need this.
Step back, somebody might say it's easier to have a larger list size, and the answer should be what? That also
no, but it's also okay. Larger list size also, yeah, but larger list size also means that that the bound on R changes. Yes, if you, I mean, increasing the list, like the list decoding GV bound is not necessarily easier with a larger list because it also posits a better dependence of the rate, like a better gap to capacity. Yeah, obviously, if you leave R the same and only increase the list size, then yeah, then you can just project into the smaller list and you're okay. Okay. Okay, so these are the results, and the time I have left, I'm going to speak a bit about how to do this sort of reduction. Okay, so using the threshold theorem. Okay, so what we know about random linear codes, really, the problem that we come down to is as follows. So fix. Okay, this should be like I going 1 to the n. So fix a type. Okay, fix partitions, and we're only going to consider now again the case where we don't impose any linear constraints between the xi's, but doing it works the same if we do impose constraints. Okay, for just for this example, assume that we have a list of partition constraints, and we want to know whether there exists in the Reed-Solomon code, whether there exist L+1 vectors with that satisfy these partition constraints, and crucially, that they do not have any non-trivial linear relations between them. Okay. If they do have non-trivial linear relations between them, then they're going to be counted under some other right. Then we don't know to F2 the L+1 here. There's going to be another vector space too that will deal with them separately. Yeah.
Those two should be Qs, right?
Yeah, we should.
I don't think 2 is at least.
Okay, I think yeah, at least this should be FQ the L+1, FQ the L+1. Yeah, I think all of my typos in this presentation have to do with right, like with F something something. It's always like I think like 4 typos all in this.
Putting a subscript.
Okay. Yeah. Okay. So
Ask the audience.
it's your fault. It's all your fault.
Parenting 101.
Okay. Yeah, giving a lecture is a lot like parenting. Okay, so never mind. Okay, so cool. So I want to show that if the degree, okay, okay, the characterization for random linear codes allows me to say, okay, if suppose that suppose that I want to show that suppose that I know that some type is unlikely to appear in a random linear code, then that means either that the degree is small of the type, or that I can mod out by some matrix B and then get something with small degree. Okay, so here I'm just assuming that I already modded out, and this is after the modding out, and then I have a type with low degree, and I want to show that if this is the case, then a random Reed-Solomon code is unlikely to contain a matrix of this type. Okay, and I want to play with this a bit on the board now for a few minutes, just to give us an intuition to how you prove something like that. And I really think that the crucial difference between this method and what AGL do is that I'm going to make heavy use of the fact that I only care about solutions like of bad tuples that don't have linear relations among them. Okay, so how does that work? Okay, so suppose a partition gives me. Okay, so suppose I have some coordinate in my code, for which, okay, so I'm going to have these tuples. Let's write them as a matrix. So I'm going to have x1, x2, all the way to xl plus 1. Okay. So these are going to be columns. So I have a matrix of dimensions l plus 1 and n. Now, suppose that the first partition tells me that the first two coordinates need to be identical. Okay. I confuse myself. Okay. Yeah. So, okay. These x1 to xl plus 1, these are words in Reed-Solomon code. So they are determined by some polynomials. Okay, so let's think of the coefficient vectors of these polynomials. With some abusive notation, let's confuse the polynomial. Okay, so these are going to be polynomials p1, p2, all the way up to pl plus 1 of degree at most k, of degree less than k. And I'm going to sometimes use them as polynomials and sometimes think of them as coefficient vectors. Let's see how it goes. Let's not call them p. Let's call them, just because I don't want to confuse these p, let's call them phi. Phi1, phi2, phi plus 1. And now, the first partition says something like this, okay? So what does this mean? It means that phi1 of something must equal phi2 of something. Of what? Of some random field element, right? Because this row is just going to, I mean, this row corresponds to some random field element. So there's some, random alpha taken uniformly in FQ, and phi1 of alpha needs to equal phi2 of alpha. And now, doing this abusive notation that I talked about, I'm also going to think about these phi's as coefficient vectors. So this is a linear constraint in these coefficient vectors, right? It's going to be a constraint that looks like phi1 times the vector 1 alpha squared to alpha k minus 1 needs to equal phi2 dot product with the same thing. Okay. Now, in general, negative degree tells me that each time so think of the process where I reveal the relevant alpha for each row, and then I add some more constraints about my phi's, my phi1 to phi plus 1. Okay? Each alpha I expose gives me a few additional linear constraints. And so specifically for this alpha, I only got one constraint because the only constraint in this partition is that 1 and 2 must equal. But in general, I can get as many as L constraints here. Okay? It depends on the relevant partition. Now, because the degree is negative, then, if everything goes well, then I expect, if everything goes well, I expect at some point to reach a part where where I have so many constraints that I have, my constraints should just cover the entire possible constraint space, and then there's only going to be the trivial zero solution to the equations that require the type to appear in the code, and then we're done. Okay, if that happens, then we're done. What's the problem? Of course, that during this process, it's possible that I expose some new constraint that's already implied by the previous constraints. And the question is, how can we avoid that? So we're going to do so. Let's start by assuming that I have my set of constraints. Maybe I'll just continue writing here. So suppose I already have an existing set of constraints. Let's call it W are going to be my constraints, existing constraints on phi 1 to phi plus 1. And now I'm going to add a constraint of the form, let's give a name to these vectors, okay? So these are going to be, let's say that V alpha, where alpha is that Q, is going to be the vector 1, alpha, all the way to alpha to the K minus 1, okay? So the new constraint I'm going to add, so let's say I'm adding a constraint of the form phi 1 V alpha equals phi 2 V alpha random alpha. Now it's possible that I'm adding a few constraints at the same time, and I'm going to discuss that in a second. But for now, let's assume that I'm only adding one constraint. So there's two things that can happen. One possibility is that I can ask what's the probability that this constraint is new, okay, that this is not implied by the older constraints. One possibility is that this, what does this depend on? It depends on how many constraints of this form are already spanned by the previous constraints. Now, here's the catch. If the bad thing that can happen to me is that there are many, that almost all constraints of this form have already been spanned. But what does that mean? That means that I'm extremely close to the case where all constraints of this form have been spanned. If all constraints of this form have been spanned, then that means that I have a non-trivial relation. I have the relation phi 1 equals phi 2. Okay? So either I'm very close to having spanned all constraints of this form, and then I'm done. Or I'm not very close, and then I just need to convince you that, or even, I can even say more. Either I've already spanned all these constraints, and then I'm done, or I haven't spanned all these constraints, but then with pretty good probability, I'm going to add a new constraint that hasn't been spanned before. Okay, so if all of these constraints have been spanned before I'm done, because I have a non-trivial relation between the phis. If not, then the space of constraints of this form that have already been spanned, it's not a full degree. So there exists some vector orthogonal to it. Let's call it, I don't know, U is orthogonal to previous constraints. And then this is going to add something new as long as the V alphas are not orthogonal to U. So we just need V alpha not to be orthogonal to U. And this is the sort of condition that we have. Well, sorry. And this is OK. This this, okay, so like I have a certain linear functional u. I'm applying it to a random v alpha, okay? And we know that the v alphas don't have, so this would be like applying a certain polynomial to a random alpha, and we know that it's a low degree polynomial, the polynomial of degree at most k, so we're not that many solutions. So the probability of 0 here is small, so we're good. Okay, so this is basically using the fact that Reed-Solomon codes have good weight or low bias to show that when I add one constraint, if I haven't already added all constraints of this form, then I'm likely to add the constraint that's not implied by the previous ones. So that's okay. But this, the only thing I use here for Reed-Solomon codes is the fact that they have good distance. So where do I need the extra structure for Reed-Solomon code? I need it when I add several constraints at the same time. Okay, so I could be adding like, something like phi1 v alpha equals phi2 v alpha, and also phi1 v alpha needs to also equal phi3 v alpha, and so on. And I want to make sure that all of these new constraints I'm adding are new together. Okay? And then I'm going to need a generalization of this to hold. So what generalization of this am I going to need? Okay, what do I have? I'm almost done with the proof. Okay, I'll be done. So if, for example, I'm adding two constraints, and now I'm going to, there's linear algebra that I'm not going to do. I'm just going to tell you the final result. It's going to look like this. There's going to be some matrix. If I added two constraints, it's going to be a 2 by 2 matrix. There's going to be, this matrix is going to look something like this. It's going to have 4 polynomials which are determined by the previously existing space. Okay, so these polynomials are going to be like psi1, psi2, psi3, and psi4, and all the psi's. Green. Okay. Okay, so I have this matrix. I'm going to apply it to some random alpha. And I'm going to apply all of these to some random alpha. And I want the determinant of this matrix to be non-zero. Okay, this is just, the case I showed you before is just the case of a 1 by 1 matrix, where I just want the entry to be non-zero. But in general, I want this determinant to be non-zero. So I can assume that these polynomials give a matrix, like the determinant polynomial of this matrix is not identically 0. And then the requirement is that this matrix have non-zero determinant when I apply it to some random alpha. Now, the thing is that the determinant of a B by B matrix is a polynomial of degree at most b times the degree of the polynomial. So it has, like, instead of degree k, it has degree bk, which is still small enough if I took my q to be large enough relative to k. And here I'm actually, and here I'm obviously actually using the structure of a Reed-Solomon code. So again, the conclusion is again going to be that as long as I'm not already very, very close to spanning all the linear relation, like to already having some linear relation be mandated for my x1 to xl plus 1, then this is the event that would allow me to make sure that the new constraints I'm adding are completely new. Okay, so we just apply that, like we continuously reveal the alphas corresponding to these lines, and each time we either get new constraints added in, or we end up with some non-trivial, or we end up with some having already gotten some non-trivial linear relation between these x1 to xl. Yes.
Yeah, I'm kind of just curious about how to kind of make sure during your argument the determinant is not symbolically 0.
So you need to. So let's maybe let's take this offline because it's yeah. Basically, you use the fact that there is at least, you know that there is, if you haven't already exposed all the, if you have, okay, the determinant is not going to be symbolically 0 is exactly for the same reason that in the single new constraint case that I showed, you know that, we know that there exists at least one possible vector that, at least one possible alpha for which the new, for which the new constraint won't will be new, because otherwise you know that you already have all the constraints. Okay, this is where we use the assumption that until the current point, there are still linearly independent solutions. Okay, so just this is the technique. Let's finish with a recap of some open problems that we discussed. So I think we pretty much discussed all of these throughout. I just wanted to list a few of them. So yeah, okay, we really want to understand list recoverability better. Okay, so if we understand list recoverability of random linear code, we're also going to get something about list recoverability of random Solomon code now. We want to break the order of n bits randomness barrier for de-randomization of random linear codes. We want to be able to handle non-local properties where the lists, for example, lists recovery with large lists, where the list is exponential in n and not a constant. We want to handle what I call pi2 properties. Okay, so for example, this toy problem with about covering. And one final thing I want to do is I want to find. Let's say keep putting. This is my. Nice Cartago. This is I put it in one different talk. I want to find the limit object for code. Cartago. Maybe I mispronounced the Latin. So limit object. Okay, so for graphs, there's something called a graphon, which is if you take if you take a random ensemble of graphs with a random graph ensemble with large n, then it's possible, a very classic, useful result, to view these random graphs as approaching some continuous object, which is very useful in trying to model what happens with these random graphs. Instead, it allows you to do continuous operations, like continuous analysis instead of discrete analysis to understand these graphs. And I really, really because these techniques about local stuff in graphs, in codes, are really inspired by stuff that happens in graphs. I think it would be amazing if we have something similar for codes. There are reasons that this should be considerably harder and perhaps impossible. But this is something that, in my view, this is something that would be amazing. I'd really like to think about it. Okay, that's it. Thank you for bearing with me for 3 hours. Thank you so much.
Thanks, Jonathan, for the great sequence of talks. Yeah, we have a few questions.
So what if you think about the linear code as kind of a Cayley graph, and then that's your graph? And then,
Sorry? What if I think of a linear code as a Cayley graph? No, because that's not what I'm trying to model. I'm trying to model the geometry. The geometry in the sense of distances between code words. The Cayley graph won't give me that because the Cayley graph would give me for the Cayley graph I need some generators, and the generators are not going to be E1, E2, and so on, because then it's not going to be the generator for code. It's going to or for an interesting code.
So the AGL result is what? Average distance list decoding, right? So did whatever we say also say something about that, or just regular?
You're asking if the theorem about random linear code.
Yeah, because AGL says that they actually achieve some average distance list decoding.
Yeah, I think it should also work for average distance, but I'm not 100% certain that.
Does it make sense to take Gromov-Hausdorff? If you're thinking about metric properties, does it make sense to take Gromov-Hausdorff limit of family of codes?
So you'd have to remind me. I think I heard the term once, but you really have to remind me what's a Gromov-Hausdorff limit.
I'll recall the definition and talk to you about it later. But it's a way to take a limit of a sequence of metric spaces.
You look at all embeddings of one metric space into another and take the Hausdorff distance between the embedding and the actual.
Okay, so may I ask you that?
Frankly, I have no idea. I need to see the definition and think about it.
Maybe from a high level question to a nitty gritty one. So in the last transfer, so your RLC theorem only required the degree to be less than 0, but I guess the thing you showed wanted it to be less than minus
The
epsilon.
RSC theorem also wanted the degree to be like, it's not exactly less than 0, it's somewhat less than 0. But yes, for the read solve, no, I think in the RLC theorem you also need some epsilon there. Just like throughout this talk, throughout these talks, in many places I
Hid the epsilon in.
I hid some epsilon gaps. Yeah.
Okay, last call for a question. Right. Great, let's break for lunch, and thanks again, Jonathan. We'll be back here at 2 as well.